Hello and welcome to the Blockaday Podcast. On this podcast, we aim to bring on experts from a wide range of industries to discuss blockchain topics simply, inclusively, and honestly so that a diverse audience can listen, enjoy, and understand how blockchain technology can benefit and empower them. And today I'm thrilled to be joined by Chris Tam, Head of Partnerships at BTQ. Chris has a Master of Engineering Science, Software Engineering, and Artificial Intelligence from Western University. And we're going to chat about a lot of cool stuff today, including post-quantum blockchain. So excited to get into that. Chris, thanks so much for being here today.
Thanks for having me. Super excited to be here.
Let's dive into you first. Sure. You're the guest of honor here today. So why don't you tell us a little bit about your background and how you came to be at BTQ and how you came to be involved in this blockchain world.
For sure, yeah. So I guess my background would be computer science is really kind of where it all started for me at Western. I did my undergrad there, and that just got me interested in the ability for computers to solve problems in our everyday lives. And I was really interested in software, but no application seemed to really break the barrier in the sense of kind of redefining how we can do things in the world, opening up new opportunities. I mean, these phone applications were cool and everything, but they still seemed kind of constrained. And so this is kind of when I had come across blockchain, and I think it was 2016. I was at a conference, completely unrelated. It was like a business conference, but there was just one dude talking about blockchain, and it really caught my attention. And and then so when I came home after that, I started Googling things and searching things up. What is blockchain? And I really dived into it. And this was around 2016, and kind of Ethereum was coming onto the scene here, and so I learned about these things called dApps and kind of a different way of using blockchain other than just as a purely financial means for compared to Bitcoin. And so I just kind of dived right into it. So then a few years later, every summer I would come home from school and just kind of read these white papers and try to understand what different blockchains are doing and what are all the there's so many ways to arrange a blockchain or to build a blockchain, and that really piqued my interest. And then eventually I just kind of started reaching out to people and came across the founder of BTQ, and kind of offered myself up to do some work for free for a few months, and eventually he just brought me on board. So yeah, here I'm at BTQ. I'm loving it, and excited to talk a little bit about that.
Yeah, the old blockchain rabbit hole.
That. Absolutely.
So I'd like to hear, in your own words, what is blockchain?
Mm-hmm. Yeah, so there's a more technical definition, which is very boring, but you could just imagine as a distributed ledger that records, it's typically transactions, but it can really be anything for everyone to see. Mm-hmm. But in my own words, what gets me really excited is the ability for blockchains to kind of redefine how humans interact with each other. And so this ability for us to all agree on some state of interactions or transactions really with other people allows us to build new applications and opens doors to all these kind of services that we hadn't had before because we couldn't all agree on the same thing.
Right. Yeah. There's so many different ways to describe it, and I think that's a really good one. Just in essence, this record-keeping technology that allows people who don't necessarily trust each other to come to some kind of agreement. And then, like you say, there's so many things that we could never imagine doing before that now we can with this blockchain stuff.
Mm-hmm.
Yeah, really sweet.
Yeah.
So you are working at BTQ. In a few sentences, what does BTQ do?
Sure. Yeah. So we're a quantum security company that's focused on blockchain. We do a pretty wide range of things, but essentially our mission right now is to solve problems at every level of the blockchain stack, with an emphasis on post-quantum security. And so this is something that I think we're going to talk about
Yeah,
quite a
yeah,
bit. This,
yeah. We'll dive into all the nuances
Yeah,
here.
for
I
sure.
just want to start, high level and kind of take us down, right?
Yeah, absolutely. Yeah, yeah.
Okay, so we say post-quantum blockchain, and that's the idea that once quantum computing gets to a certain stage of development, blockchains as we know them today face an existential threat. So let's start with what is quantum computing, and how does that impact blockchains of the future?
For sure. Okay, so first of all, I'm no quantum computing expert.
Well, neither am I. So let's dumb it down for everyone.
Sure. So quantum computers compared to classical computers, and by classical I mean the computers that pretty much all the computers that we use today. Quantum computers use a different bit than classical computers. So quantum computers use what are called qubits, and classical use classical bits. Now classical bits are restricted to two states. They're binary, ones and zeros, whereas qubits they have two states, one and a zero, but they can also be in a superposition of those states. And what that allows you to do is when you start combining lots of qubits together, is it exponentially increases the computational power of these qubits because they can be in multiple positions at once and can store vastly more information. And so what researchers have seen is that certain problems can be solved that were previously infeasible for classical computers to solve. Sorry. I think a really good example of this is a Canadian company just over the summer, I think it was June, called Xanadu, where their researchers demonstrated what's called a quantum advantage, which is basically a breakthrough in some problem using a quantum computer. They were able to solve a problem that would have taken a classical computer over 9,000 years to solve. And their quantum computer did it in less than a second. I think it was 0.36 something. It was a fraction of a second. And so that speaks to the exponential scale of power that quantum computers can bring, but then also the threat that they pose to our existing security infrastructure. So a lot of our security, our digital security, depends on the difficulty of basically solving certain math problems. And the Xanadu example just shows that certain problems that we thought were unbreakable are now breakable, and that is cause for concern when it comes to digital security.
So the main thing is the idea of cryptography, right? Mm-hmm. And then specifically in the context of blockchain, I mean in many other systems, but you guys are focusing mainly on blockchain, right? So
mm-hmm. Yeah.
Taking these blockchain systems, what makes them so secure is this typically this public and private key cryptography that allows users to have this self-custody of their assets. Mm-hmm. So can you maybe talk a little bit about how that works? Because as I understand, that's kind of the main thing that quantum computing can affect and interfere with, is that public and private key cryptography, and that renders blockchains less secure.
Yeah, absolutely, for sure. So maybe a good way to frame the importance of public key cryptography is we'll start at a very high level and kind of abstract away the technical details. So we've said that quantum computers threaten the security of blockchain, and that's particularly they threaten the public key cryptography security of blockchains. And so let's just speak first to the significance of public key cryptography. So basically, there are algorithms which exist that can render blockchains practically useless because they threaten this public key cryptography. And so how we can think about this from the user side is, if you can't trust that your funds will be safe, then you can't use this blockchain. If you invest thousands of dollars or start generating income or use this day to day, and you can't be sure that those funds will be there tomorrow, you're not going to use it, and nobody will. And so this public key cryptography is what keeps users' funds safe. And so now we can dive into kind of how this works. So public key cryptography consists of really two keys a public key and a private key.
And what is a key? Like, what does that look like?
Yeah, so it's really just a series of alphabets and numbers, but it's essentially, you can think of a hash that you can't know. It's a secret. So, well, it depends on whether it's a secret or if it's the private key or the public key, but it's essentially your ID or your passcode in some sense. And so in public key cryptography, we have this private key, which holds all of your funds. And then you have a public key, which you show to the world and you sign transactions or interactions with, so that people know that this is coming from you and not somebody else. And how quantum computers threaten this public key cryptography is that, given the public key, which everybody has, which you show to the world, a quantum computer would be able to derive the private key from the public key, thus giving the attacker access to all of your funds and really the power to do anything and really disrupt the blockchain and the consensus in the blockchain. Yeah, so basically quantum computers attack the private key given someone's public key.
Right. Yeah. So very simply, when you're securing your crypto assets or whatever data is on the blockchain, you have this private key, which is the password, and you have the public key, which is kind of like your public address, like an email address is a good way of looking at it, right?
Yeah.
And then through quantum, generally, it's impossible for anyone to figure out what your private key is, but with quantum computing, they can derive that private key from the public key because these computers are so powerful.
Exactly.
In essence, that's the idea, right? So
exactly, yeah. And if we wanted to dive a little bit lower into the specific mechanisms that are at risk for the audience that is interested about this, it's the elliptic curve cryptography that's particularly at risk. So public key cryptography is this subject, and there are different ways of implementing it. Ethereum, Bitcoin, Solana, pretty much every major blockchain right now uses some form of elliptic curve cryptography. And it just so happens that, well, maybe not just so happens, but it is true that there are quantum algorithms that can attack this specific implementation and derive a private key from a public key.
Mm-hmm. Mm-hmm. And this is a question that I think is kind of like quite debated. How many years away are we from quantum computing actually posing a real threat to these blockchains? Like how far are we from someone can fire up a quantum computer and just steal my money like tomorrow? Like how far away are we from that?
Yeah, so this is a hotly debated subject. From the researchers that I've spoken to, we're estimating you would need several thousand qubits to break the current encryption scheme for digital signatures. And right now, I think we're at 128 qubits put up by IBM, or that's their projected I guess number of qubits by the end of 2022. And we are seeing somewhat of at least in the projections and looking back from 2012, if you plot out the number of qubits that scientists are able to use, then you are starting to see this very similar to Moore's law, an exponential increase. And so from that, you might think that it may not be long until we're able to break this, but then there are other problems in the way. Turns out that the more qubits you use in a quantum computer, the more they interfere with each other because of property of quantum mechanics. And so there's a lot of what's called error correction that needs to be solved. And this is a huge topic amongst the quantum computing research community. Google's quantum AI summit I think they dedicated an entire summer symposium to pretty much error correction. So this is definitely on the forefront of researchers' minds. It's difficult to say. We can reasonably expect a quantum computer with sufficient qubits and error correction to break blockchains within the next 25 years. But I think that's a relatively conservative estimate. we might, depending on how research goes, it might be on the scale of 10, 15, maybe even less.
Right. There could be some like crazy breakthrough like tomorrow for all we know that could accelerate this kind of thing.
Yeah, absolutely. Yeah. And there's a huge amount of investments and incentives for people to build and to improve quantum research. So yeah.
And something interesting beyond just like the threat of it actually being like physically possible. So just yesterday I had a like little Q&A session with Chen Mao from your chief scientific officer from BTQ, and I kind of we were talking about a similar topic, and something that he raised that was super interesting was it's not just like, again, the idea that it'll eventually be physically possible. It's that even today, like, people can start to have trust concerns, right? The fact that this is something that is feasibly possible, and at any given moment, potentially it could be something that can be implemented. Now we're at this case where, like, how people can start to like claim that, oh, I didn't actually sign this transaction, right? If we're getting to the stage that, you know, however many years down the road, or even sooner, that this stuff can be used to derive private keys and essentially access people's accounts. Now there's that trust issue, and if we're starting to lose trust in blockchains, even if physically we can't quite get to that stage yet, but if the trust is shaken, the whole thing is built on trust, right? Like the whole idea is trusting something, this network, because you don't trust the people in the network, right? And if we lose that trust, the whole thing becomes useless.
Yeah.
So I thought that was an interesting insight, and kind of speaks to like the urgency even more so of like trying to like that, for example, what you guys are doing to try to solve this today. So on that topic, tell me a bit about BTQ. Like, what is the vision and the mission of BTQ, and how are you guys working to solve this quantum computing problem that we just talked about?
Yeah, for sure. So we're as I described BTQ earlier, we have a wide range of projects, specifically on the security, on the concern of security. We're building blockchain infrastructure that's equipped with post-quantum cryptography. And so what post-quantum cryptography is essentially the same kind of cryptography that we use in our classical computers, except that it's basically equipped with this armor such that it's theoretically secure against quantum attacks. And so if you're building, as we said, as you just described, if you're trying to build a blockchain, or you're trying to adopt users onto a new technology, and there's any concern that this technology won't be relevant in 5, 10, 15 years, then it's going to stop a lot of people from being willing to hopping on board. And so, yeah, we're building at this infrastructure level blockchain solutions and software and security to equip our own blockchain and other blockchains with post-quantum security, so that we can continue this huge experiment of seeing what blockchain applications can do. Yeah. We're also working on some other relative, I think they're important problems, less to do with security, but I'll just touch on them. Working on eco-friendly mining for proof of work schemes, because we've seen a huge kind of pushback from or against proof of work because of the environmental concerns, of basically due to miners using insane amounts of electricity to sustain a blockchain. And so if we can come up with a scheme to lower the energy costs for the entire mining pool, then you could have a proof of work blockchain without those same environmental concerns. And that also kind of plays into security, because you keep a larger base of you basically retain more decentralization with the more miners you're able to have. And if there are fewer miners who are excluded because of the energy costs or dissuaded, basically if you're able to maximize the number of miners that you have in a blockchain, then that increases the decentralization and security of the blockchain. So we're doing that, and then also at the more user level, where you're building ZK or zero knowledge apps, which is this very interesting and kind of, it's becoming more popular especially in the Ethereum community, these zero knowledge rollups and such. And And so so we're essentially building this like a software tool set for users and developers to build applications that respect privacy and kind of respecting this Web3 tenet of user or of internet freedom. Yeah.
Awesome. Really cool stuff, which is why I'm so stoked for you to be here to chat about it. So I do want to talk about the cryptography piece, the efficient block space idea, right?
Absolutely, right.
But before that, I wanted to just briefly touch on the other two things because they're a bit less, I'd say, relevant to the discussion at hand. So just some things that are coming to my mind here. So we're talking about the energy efficient mining.
Yeah.
Okay, so I just wanted to ask you. So Ethereum is currently a proof of work blockchain, meaning they have these miners using enormous amounts of energy to reach consensus and keep the blockchain secure and validate transactions. But they're moving to another mechanism called proof of stake, which they're saying is going to cut the energy cost by 99.5% or something crazy like that. So, and then a lot of the other mainstream blockchains today are already proof of stake. So we're getting to the point where only really like Bitcoin is like one of the big ones that is going to be operating as proof of work. So I was just wondering, like, what's your take on, if you have one, on proof of work versus proof of stake? Like, if the transition to proof of stake is something that all these blockchains are going towards, and if this is so energy efficient, like, why are you pursuing energy efficient mining?
Yeah, it's a great question. Again, so yeah, this is a pretty hotly debated topic between proof of stake and proof of work, the benefits between the two. Proof of stake, it comes with its own downfalls as well. So you need to, the way it works is essentially you need to stake a significant like amount of ether or ETH in the case of Ethereum.
What is staking? What does that look like?
Yeah, so it's literally putting it up for like willing to be sacrificing a significant amount of ETH in order to validate new blocks. And the idea here is that you will remain like trustworthy and you will like not try to act maliciously against the blockchain to validate new blocks, because if you do, you're going to be penalized heavily. And so it's literally staking your ETH to validate new blocks rather than spending a significant amount of electricity to validate new blocks. So it's the same mining mechanism, but instead of, you're basically swapping out electricity with cryptocurrency. And the downfall of that is that you, like, as a staker, you need to be wealthy enough to participate or to provide enough ETH to stake these or to validate new blocks. And so that excludes a lot of people from this block validation process. And what that does to decentralization is it kind of curbs it down to basically a specific group of people who have enough money. And so the proof of stake, the way it's implemented on different blockchains will vary, but it seems to be the case that it does have a negative impact on decentralization. And so the reason that we're pursuing this proof of work is because it's a tried and tested methodology, and we've seen a lot of successful blockchains being able to have a good like a minimum threshold of decentralization using proof of work. But then, of course, addressing this environmental concern, and if we're able to mitigate that, then we should be able to have as wide of a base of miners and thus decentralization as possible compared to some proof of stakes.
What about the fact that in proof of work mining, typically there exists large economies of scale, and like you say that proof of stake, if you need enough resources to participate in the system, is it not the same for proof of work? Like, isn't it technically infeasible for like me to go set up like one like mining rig, and like I'm not gonna earn any Bitcoin if I'm just like mining in my basement, right?
So I mean, I think that there's like huge like Reddit threads on how to on how to set up a mining rig, and it seems like it's like there are a lot of basement miners who are able to earn passive income, mining from the comfort of their own home. And I don't think that trend would change too much, especially given that like we've already seen one generation of Bitcoin miners. And so that generation would be well equipped to, would have the knowledge required to set up their own mining rigs and kind of, they could even use the same mining rigs and transition to BTQ eventually. And so, yeah, I mean, that's a good point, because there always is this barrier to entry. But I think the cost of buying a mining rig is less than the stake you'd need to mine Ethereum, for example. So I think Ethereum, the last time I checked, it was at 30. You would need 30 ETH times whatever the price of it is now. It would probably be like somewhere around 60,000. Yeah.
Okay. Yeah, I was just curious about that. I do think that there is a lot of value to energy efficient proof of work for sure. I think that a proof of work is an important thing for us to keep around, because yes, proof of stake, they both have their problems, but proof of stake maybe has more. But I think the concept of proof of work is so much more interesting. It makes blockchain seem so much more like this, analogous to like a natural resource, and I think it's really cool the way it's generated like that. But the big problem being that it is, Bitcoin literally uses as much energy as, I think in the ranking of like energy uses, if you consider Bitcoin to be a country, it's in like the top 30 or something like that. It's a big energy hog. And then there's like the philosophical question, like how much energy does a global censorship resistant borderless monetary network deserve to use? But if it can use less, then I think that's for the best. So I just wanted to dive in that a little bit.
I love it.
So let's talk about the other thing you're doing. So I'm going to try to describe how I think it works, and then you can correct me because I'm probably wrong. But so
happy to.
So when you have these blockchains, which are chains of blocks. So that's the way the data is structured, and each block typically can only hold a certain amount of information, right? And they have a limit on the size. And if the effort it's going to take to upgrade these blockchains to be quantum resistant is going to vastly increase that block size in such a way that it becomes infeasible for these things to operate as they're currently working. So what you're trying to do is create some kind of software algorithm that will allow these block sizes to remain small while also being quantum resistant. Am I kind of on the right track there?
Yeah, definitely on the right track. Just a small detail in what's being expanded specifically. So coming back to this public key cryptography, how you have a public key and a private key. Basically, both like your public key is going to, which is broadcasted to everybody, is going to vastly increase in order to be quantum resistant, in order to not be able to derive a private key from your public key. So you had it, apart from that, mostly correct. It was because of these larger key sizes, you're going to have either larger blocks which get processed less frequently. So basically that impacts your transaction time. You have to wait longer for a block to be validated before your transaction gets processed on chain. Or you keep the same block sizes, or somewhere about that, and you have fewer transactions in them, and so that will also make like slow down transactional speeds, and also increase the gas costs or the transaction fees per transaction, because it's just a more competitive block. That's really the fallback from, or that's the implication of moving to quantum resistant signatures, or to post quantum cryptography. Basically, it kind of takes us, like, we move one step forward with security, but then two steps back with scalability and speed, and then there's some other consequences as well. So if we're able to mitigate this, if we're able to keep security and then also keep everything else that we have on the table, speed, let's just keep like speed and transaction fees, then that means that we're actually moving in the right direction, and that means that we can keep blockchains in the face of quantum computers. And so what we're doing is basically we've come up with this compression algorithm where you're able to use these larger post-quantum signatures without sacrificing the larger block size or fewer transactions in a block. So you can basically think about it as just keeping the same blockchain structure, but with the addition of quantum security.
Mm-hmm. Okay. Cool.
Yeah. And so the way that we do that is really mostly a zero knowledge technique, and this kind of opens the door for us as well to dabble into other ZK applications. We have a post quantum security solution that is made practical and feasible in blockchains via zero knowledge, and that opens up the door for us to use the same kind of zero knowledge techniques in other industries, but then also to help other blockchain companies move to post quantum or upgrade the security without sacrificing the user experience.
Right. Yeah, because even if it's quantum secure, if we lose that scalability and that efficiency, then blockchains are already like relatively inefficient to other kind of ways of storing data, right? So we want to kind of have these things as scalable and as efficient as possible.
Yeah. So, yeah, exactly. And so the thing about blockchains is that because it's decentralized, that means if you're running a full node, that means you need to store every single block on the blockchain. And if that blockchain is far larger than it is today, that's going to make it more inaccessible for more people to run full nodes, to mine it, and to validate transactions. And so again, this kind of plays into the decentralization of the blockchain. A larger blockchain would make it it would make it more centralized, because there would be fewer people able to have the memory requirements to store and monitor a full blockchain.
Right. Yeah. When we say full node, that's just like one of the many computers around the world that's storing like an entire copy of the entire history of the blockchain,
Exactly.
essentially from the beginning until now, the record of every transaction ever. And if you increase the block size, then you have these enormous memory requirements. You need terabytes and terabytes to actually feasibly store this, and then it becomes less accessible for people because not everybody can afford to have that storage space.
Yeah, exactly. And so we ran some experiments, and basically there was. So we talk about post-quantum signatures and the increase in block size as a result of them. Mm-hmm. There was this huge competition in the US called the NIST post-quantum cryptography competition. NIST, just for some background, is a government organization that basically sets the technical standards and regulations for companies and government agencies around the US, and is largely seen as the kind of like source of authority for the minimum security requirements companies should implement in order to be safe. And so NIST started this competition to find post-quantum cryptographic algorithms that would be secure for this digital signature paradigm. And basically, they started in 2016, and it had ran for. It's still on today, but they standardized 4 algorithms that are post-quantum secure. And so what we did at BTQ was we ran experiments to see how large blockchain ledger sizes and key sizes would increase as a result of implementing these new NIST PQC algorithms. And it's remarkable how much they increase by. At the minimum, they'll be with the smallest key size that was a candidate or that was approved by NIST, it would increase by 20 times, and it gets up to over 100 times larger. And so that has pretty significant consequences on who's able to run a full node. And so what we're really trying to do is to compress these signatures so that we can avoid this 100x increase in ledger sizes and key sizes.
Are you able to explain like how that works, like in a way that my little brain could understand? Like how I get it fundamentally that you're trying to like compress these keys to keep the blocks smaller so that the and more people can actually store this data on their machine. But like how the heck does that actually work in practice, if you can kind of keep it high level?
Sure. Yeah. So I can use an example that maybe more blockchain users will be familiar with. So on Ethereum, we have they're called L2 scaling solutions, or they're also called roll-ups, where the mechanism there is that you take a set of transactions and you roll them up into a single hash that represents this set of transactions. And then you only publish that one hash on the blockchain. And so what that does is it massively increases the speed of blockchains, because you're able to process 1,000 transactions in one transaction, and you can even layer them on top of each other. And then it also decreases the transaction fees associated with all those transactions. And basically, that one fee would be I guess the transaction fee associated with that rolled up hash would be distributed across all of those transactions. So that's the roll up technique, and we're doing a very similar thing, but instead specialized for post-quantum signatures. And so that's kind of where our technicality and expertise comes in, because it's a non-trivial problem to roll up these post-quantum signatures in the same way that you roll up classical signatures or pre-quantum signatures.
And so it's a lot of scientific research and experimentation that you guys are doing. Is that kind of like the one of the main processes that your organization does?
Yeah. We're definitely a research-oriented startup. Most of our employees are scientists and cryptographers, and we've many engineers, but really our team started off as a team of post-quantum cryptographers, and that's really close to the core of our identity. And so because we're a research-driven startup, we like to kind of like focus on scientific applications of blockchain as well. So there's this new, or maybe not new, but like a growing space of what's called decentralized science that we're very passionate about and very interested in, and spending a lot more time building DeSci projects.
Since you bring that up, why don't we talk about that? Because I think DeSci is such a cool use case of blockchain. It's something that I don't think it's very mainstream. You know, everyone loves to talk about cryptocurrency and NFTs. You know, your DeFi, GameFi, DAOs. Like those are kind of the hot topics. And then there's a bit of people knowing about blockchain's use case and things like supply chain. But this DeSci thing, decentralized science, it's not very well known, but I think it's so cool. So why don't you kind of tell us what that movement is all about, why it's important, what problems it's trying to solve?
Yeah. So decentralized science follows the same idea as like DeFi, for example, creating or bridging the financial industry onto blockchain and finding new applications on blockchain. And so what decentralized science is doing is basically taking like research work / scientific work and building the rails on blockchain so that we don't have to rely on these previously centralized authorities to, say, publish research or to gatekeep research from a lot of members of the public. So one example of this would be rearranging the scientific publishing model, for example, where if you're a researcher and you want to publish a paper, you need to go through one of a few major publications to get your work out to the public. And they're really seen as gatekeepers of scientific knowledge. These researchers have to pay an enormous amount of money to release even to release their work in a journal, and they have to pay even more to release it publicly as like a available PDF for the general public. And the way that this is set up is basically is just the status quo. It's kind of this accepted methodology of getting research out into the world. And with blockchain, we can disrupt how this works. So we can place the power more. Place the power more in the hands of researchers, and I guess researcher communities to basically earn the capital required to do good research, because they can be compensated for the research that they produce, and they can also raise money from the general community rather than just universities or research grants to do interesting research. So it also changes. So it changes the way that we release research, but it also changes the way that research is done.
Mm-hmm. Yeah, I was doing some reading on it, and I saw that like one statistic was that scientists can spend up to like half their time just doing like fundraising and trying to like do these like grant proposals. Right. So if ideally scientists should be doing science, not filling out onerous like multi-page documents trying to get money. And then the other issue was, like you talked about these paywalls, that like the whole idea of science is supposed to be, in my opinion, this like open thing that, humans do this research to discover things about our world, and that should be openly shared with everybody. But for some reason, you have to pay hundreds of dollars to access these, or thousands of dollars even to access these studies, right? And then that leads to all kinds of, I think, like, incentive issues. And, I've heard about hacking, where like you're incentivized as a scientist to try to get like a statistically significant result to your experiment, because those are the things that tend to get published in these journals, and those are the ones that make it easier to raise the funding. And then you get these skewed results where like, what the heck are we even doing here in the first place?
Right? Yeah, absolutely. So I think there's something called the reproduction crisis, where basically scientists spend all their time reproducing experiments, which is a good thing, but it also leaves a large amount, or a large space of research opportunity unfulfilled, because there's not the right incentives to pursue that.
So on like an example of DeSci that I saw, just randomly searching the internet. One thing that this particular scientist, I can't remember where he was from, but he raised the problem that it's hard to kind of get funding for like smaller projects. Like most of these grants are for like larger research studies. And so he said a solution for that is like blockchain-based crowdfunding. So what he did was he had a crowdfund for, it was actually for a quantum-based project. So it was like a quantum token. And he wanted to raise like between 3 and 10 Ethereum. And if you participate in the crowdfund, you send Ethereum to the smart contract and you receive these quantum tokens back. And then if he reached the fundraising goal, which he did, so I'm excited to see kind of how this goes, if what gets released, he would take the money and pay like a research assistant for the term to do the experiment for him, or whatever it might be. And then all of the data gets published to the blockchain, there for all time, for everyone in the world to see forever, for free, right? And then also he was going to mint, or he was going to create an NFT of each like kind of individual piece of this research, and then put that up for sale. And the idea was any NFT sale, the profit from the NFT sale would accrue to the token holders. So you're kind of investing in this scientific experiment. And then if there's interest in purchasing these NFTs, this kind of on-chain record of this science, you actually get financially rewarded for that. And then this crowd fund was open to literally anyone in the world with an internet connection.
Yeah.
So I think it's such a cool use case, right? And then really showing like the power of blockchain and how it can really let us do things in a new way, not just new, but more open and transparent and fair, and ultimately more beneficial for the world at large, right?
Yeah, exactly. I think you hit the nail on the head there. It really changes how, like, the incentives for, in this case, new research to be published, because if that scientist relied on the traditional research or grant model, where you need to apply for grants, typically from universities or from governments, they would only approve projects that are in their best interest. Whereas if you can all of a sudden crowdsource funds to fund research, then you can kind of introduce DAOs as well, which are interested in solving some problem, and maybe that DAO doesn't have the scientific knowledge or resources, but they have the capital to provide funding for those projects, and then research gets done in that area, and you have this kind of explosion in the opportunities for new science to be published.
And an opportunity for individuals to kind of choose which areas of science they'd like funded, because a lot of this funding comes from like universities and institutions like that. So technically, you are, as a citizen, like paying with your tax dollars for this science to be done, but you don't actually have a say in what is being researched, right? Like those are these institutions that get to decide that on your behalf. So if we kind of decentralize that, then I, as an individual, can choose where my money goes to further science and whatever thing I find the most interesting.
Yeah, absolutely. Yeah, and then there's this aspect of ownership as well, where you have a piece in history for contributing to, like, personally to this piece of work.
Yeah. Oh man, you can take that so many places. That's just so cool. Yeah, I could nerd out about that all day. I think it's such a
it's
cool
fascinating,
thing.
absolutely.
Yeah, definitely. Okay, cool. DeSci, look it up. It's really awesome. Let's jump back to BTQ. So first, let's talk. Let's go to you specifically, Chris Tam. So you are the head of partnerships at BTQ. What do you do? Why do you need partners? Who are they?
Yeah, for sure. Yes, yeah. So as I've said, BTQ is mostly we're a research driven startup, and so we need to reach out to a lot of to the scientific community to basically share ideas and to improve upon them, and kind of relate all this science back to the application of blockchain. So my work can be seen as a bridge between academic institutions and then industry / blockchain. So maybe this triangle between getting researchers work out into the world, and then having practical. So first of all, providing them the immediate financial incentives to get their work outside of their university labs and into the industry, and then also with this larger goal of contributing towards improving blockchains. Yeah. Okay.
Great. Who are you reaching out to these days? Like, you got any new partnerships you're pursuing, or what's that looking like?
Yeah. So yeah, lots of universities, and then also reaching out to so we've been focusing on a lot of post-quantum cryptography. These new partnerships are focused on quantum engineers who build quantum computers or who devise new quantum algorithms, because right now we've kind of taken the position as the security solution to quantum computers, but we also see the power and the application of quantum computers. So we also want to broaden our reach to build quantum computers that can also help blockchains and companies and people. So reaching out to to them. And then also a lot of other interesting companies, blockchain-based companies in the space. So a very cool one called Holonym. They were founded by founders of OpSci, who's a DeSci startup. And what Holonym is doing is they're working on a identity protocol to basically bridge your identity from the Web 2 world to Web 3. And so this is a very important problem. So if we take the example that we used for the researcher who was crowdsourcing funds from the blockchain community to do research, people need to know that this researcher is who he is and that his identity isn't being spoofed. And we have a lot of internet infrastructure set up to make sure that you are who you are, right? So we have, like, in science, there's the orc ID, but you also, just for everyday people, maybe for artists, you have your Instagram account, your Facebook, your Google account. And basically, if you can aggregate these identities into, or if you can associate those identities into an address or an identity on the blockchain, then you can take all of the credit you've built in the traditional internet world and board that and bring that onto Web3. So you can keep doing science in Web3, or you can keep doing art or being a musician, and all these interesting applications. So Holonym is a very, very cool company that we're working closely with.
Cool. Yeah, you could do a whole podcast on that topic, that decentralized identity or decentralized society, I've heard it called as well. I think again, any you put D in front of anything, and I think it just opens up so many cool possibilities, right?
Yeah.
So BTQ trying to solve the quantum threat to blockchains today. What does the future look like for BTQ? What are you guys working on in the next year, 5 years, etc.? And then say you solve the problem. Maybe we get to the point. Okay, now we have these efficient quantum-proof blockchains. Now what are you guys working on?
Mm-hmm. So we're focused a lot on privacy as well. So we see not only security as a problem, but also for the more general adoption of blockchain, privacy also needs to be addressed, because as of right now, you could theoretically backtrace every transaction from every user and associate them with an address, and then you'd be able to profile them and kind of recreate this Web 2 ad-based, kind of like customer segmentation model on blockchain. And so if we can improve upon that using with a focus on data privacy, then that would be a better step. That would be a good step forward from this Web 2 land. So focusing a lot on data privacy via zero knowledge, and then also building basically sustainable mining hardware equipment.
Can you briefly tell me what zero knowledge is? You brought it up quite a few times. I think once you explain it, the name makes a lot of sense, but in your own words, kind of what is zero knowledge?
Mm-hmm. So it's a way to share a secret with someone, or to share some information with someone without revealing all of it. So I could tell you, or let's take a maybe more practical example. Let's say that somebody wants to take out a loan from a bank, and the bank needs to make sure that this person earns some amount of some minimum amount of income in order to grant them that loan. What zero knowledge would allow you to do is communicate that person makes enough money to get to be approved for the loan, without sharing with the bank exactly how much money they make. And in the same way that maybe if we're looking at decentralized voting, and you need to be a resident of, let's just say, the state of New York, you would be able to prove to that, let's say, DAO who's running this decentralized voting system that you are a resident without revealing your address or how old you are or your gender, anything like that. Mm-hmm.
Yeah. Yeah, very, very well explained. Great analogy. Love it.
Cool.
Yeah. Okay, a couple more questions for you. So, going back to the idea of post-quantum blockchain and this, pretty urgent need to start implementing this technology because we are not too far away from blockchains potentially being rendered obsolete. How can I or like listeners or the average person like help with this problem? Like what can we do? How can we spread awareness? What should the average person do to help BTQ with your mission?
Oh yeah, interesting. Well, I'm not sure if so like maybe if you're a user of blockchains, then you like the way that you can serve your self-interest is by making sure that I guess you kind of understand what that blockchain is trying to do to protect you, so that you don't get stolen from or so that you don't lose trust in the system. And so I think like maybe keeping up to date with some of the important news updates from whatever blockchains or applications that you use is important. For example, Vitalik Buterin released an ETHCC a roadmap that includes post-quantum everything for the infrastructure, for Ethereum's blockchain infrastructure, and that's a very good sign because that means that community is thinking about it. And I guess if you are a member of a community that where that hasn't been discussed yet, you may want to bring that up and discuss the importance of being secure for the next 15, 20 years in order to keep people's trust in blockchains, so that we can keep running these cool experiments.
Yeah, future proofing it. I took a look at the roadmap for Ethereum you're talking about, and it does have post quantum everything, but it's kind of interesting. It's like the very final thing on the roadmap, way down in the corner here.
Yeah.
Do you think that's like appropriate, or do you think that shows kind of like a lack of urgency regarding this issue?
Yeah, so Ethereum has a lot of problems because of how many users it has and how many applications are run on top of Ethereum. And so it kind of makes sense that isn't being prioritized right now. It probably shouldn't be an afterthought, but I also understand that Ethereum has a lot of other problems right now. And so what's cool about this is that you can have other companies working on post-quantum everything, so that Ethereum doesn't need to dedicate a whole set of engineers to work on that.
Right. Shout out BTQ. Okay. So my final question is going back to you, Chris Tam. What does the future look like for you? Like, what are you working on next, either at BTQ or outside of it?
Yeah, so I think it's really trying to find more applications of blockchain and to kind of make a breakthrough in terms of widespread adoption. Obviously, we want to make sure that everything is safe and usable, and that takes a lot of work. So trying to push the bounds and seeing what needs to be built next on blockchains is my primary focus. And yeah, working with companies like Holland is very exciting, and obviously BTQ is doing great work. So finding other partnerships to work with so that we can make blockchains sustainable for the future.
Inspiring. Any final thoughts or comments that you wanted to share with the millions of people listening?
If you're interested in first of all, if you're just interested in blockchains but don't are scared by them, just try to have fun learning about them. If they interest you in any way, then take a dive, because blockchains are so multifaceted. You could look at it from a technical perspective, but then also economic or philosophical, and with all these new industries being built on top of blockchains, if you're a lawyer, you can look into the applications particular to your work. So I think I would try to encourage everybody to look into how blockchains might be able to change your life or your industry. And then if you're also looking to break into it, start reaching out to people. I mean, there's so many companies in the space who are trying to build things, BTQ included. So yeah, if you want to get involved, reach out to me, and many other companies are looking for cool minds to bring a new perspective.
Great. Awesome note to end things on. Thanks so much, Chris. Really appreciate you being here. This has been a lot of fun.
Yeah, thank you so much, Christian. Really appreciate it.
All right, cheers. This has been the Blockaday Podcast. If you enjoyed, please like, subscribe, rate, review, share with your friends, etc., and help us spread the word and continue to educate people about this really cool blockchain stuff. Bye-bye.